Hello, and welcome to today's Environment and Energy Leader webinar titled Complete Onsite PFAS Treatment in Aqueous Streams, Bridging the Gap Between Concentration and Destruction, sponsored by Montrose Environmental. My name is Jessica Hunt, and I'm the Director of Events for ENA Leader. First and foremost, thank you for being with us wherever you are in the world today. In case you are unable to join us live, this event will be available on demand within a few hours. If you are having any technical issues during today's event, please troubleshoot first using the Q&A widget at the bottom of your console. If you are still having issues after performing those steps, please send a message to me via the Q&A chat widget. Attendees do have the ability to chat with each other, so please say hello, let us know where you are from. To utilize the attendee chat feature, you may have to double click on enter your message. If you have questions for today's speakers, please submit over the next 50 minutes or so. Both presenters will be speaking for a majority of today's webinar, but we will have time for a short Q&A before the top of the hour. All questions not answered will be submitted to the team at ETC2 and Montrose Environmental. At this point, I am going to turn the presentation over to Dave and Erica, and I will be back on with Erica to answer as many questions as we can later on. Enjoy the presentation.
My name is Dave Campisi. I'm excited to be presenting to you today with Dr. Erica Houts. We're going to be speaking about complete on-site PFAS treatment in aqueous streams. And the subtitle to the presentation is Bridging the Gap Between Concentration and Destruction. So I want to thank you both for your attendance and your attention, and I'm excited to present to you today. To do so, I'm going to follow this agenda, which looks something like this. Conventional PFAS treatment oftentimes results in waste that needs to be dealt with, and a more sustainable approach is the use of the technologies we're going to discuss today. And to do that, I'll first lead off with an introduction to Montrose Environmental Group. Then I will briefly talk about the PFAS problem, and then move into the meat or the heart of the presentation, which will be a treatment train approach and using a regenerable resin product that will result in significant waste reduction, or a foam fractionation technology, or a combination of the two, and making the link then to a destructive technology that Dr. Houts will talk about, both providing, the strengths, the limitations, and just an unbiased approach. And I think you'll really appreciate that portion of the presentation as well. And then finally, we'll talk through and address just some roll-up thoughts and ideas and some discussion. But in full transparency, I won't be there. I have a pre-existing engagement that I could not break, so I do apologize ahead of time for that. But at the same time, want to offer my email address, which will be at the end of this presentation. So please reach out and contact me with any questions and or further discussion that we could have, and I would look forward to that. The graphic on this slide is full of colors, and everybody likes colors, so that's why I put it there. No, actually, I won't talk over this because I have a better block flow diagram in a couple of slides, and this is I'm talking about the regenerate solution kind of picture here, cartoon, other than to mention viewer's upper right hand, which is the Sorvix Repure media that we use for the regenerable ion exchange resin process. Has desirable properties, chiefly the desorption efficiency and the ability to get the PFAS off of the resin so that we can use it in subsequent treatment cycles. All right, Montrose Environmental Group and ECT2, who are we? We are a rapidly growing American corporation that is investing in U.S. technologies, and we have over 2,700 employees, 2,200 of which are in the scientific, in the technical realm of things. And you can see that that includes over 50 PhDs. We are listed on the New York Stock Exchange with an IPO date of 2020. And MEG prides itself in investing in disruptive technologies in the environmental front, one of which is the regenerable resin process that emerging compounds treatment technologies brings to the table. ECT2 was purchased or came underneath the Montrose umbrella in September 2019, chiefly because of that regenerable resin technology, which I'm going to talk to you about today. Montrose is bigger than just ECT2 because it has CTEH underneath the umbrella, which affords us emergency response capabilities as well as toxicological expertise. But we also have enthalpy analytical. We also have air sampling capabilities. We also have consulting expertise. So there is a wide variety of talents and offerings that are provided by Montrose. The PFAS problem statement, and PFAS seem to be ubiquitous in the environment, and we come across news about PFAS each and every day. And so it's a dynamic moving front that encompasses, right, the regulatory framework as well as the toxicological underpinnings, as well as advances in remediation technology, as well as the analytical conundrum to get to parts per trillion, to get to parts per quadrillion, and the challenges associated with that. So all four of those facets affect one another, which provide challenges in this space, but make this space, dare I say, fun, but certainly fast-moving and engaging. Generally speaking, traditional technologies to remove PFAS from environmental matrices include granular activated carbon or single-use ion exchange resin or membranes, all of which are concentrating technologies which generate a waste stream that needs to be dealt with. And that waste stream, there's issues associated with that waste stream, particularly in light of the proposed notice of proposed rulemaking to make PFOA and PFAS circulate designated hazardous substances. So circulate designated hazardous substances can then drive additional requirements like the Department of Transportation classifying them as hazardous materials, which require increased transportation costs, which would then result in increased disposal costs. So the ideal way to move away from some of those increased costs would be through eliminating that waste, which can be done through the Montrose solution, this regenerable ion exchange resin, or foam fractionation, and the destructive technologies that Erica is going to speak about. But you also have issues associated with future liability, and how do you quantify or put a cost on avoiding future liability associated with just avoiding generating this waste in the first place. Alternatively, you could have leaking landfills or treating the landfill leachate and the liability concerns that might go along with those in future years. So there is also a peace of mind that should be associated with the waste minimization component. Which there are other advantages, which are listed on this slide, and you can see 75% reduction in costs. That's not for every case, but it is for some cases. And so if you're talking about micrograms per liter of PFAS, we should have the conversation. Micrograms per liter will afford you, the cost curves will cross. I'm not sure if they're going to cross in 2 years time frame or 15 years time frame, but when you're treating for those longer periods of time, and you have the environmental social governance issues associated, benefits associated with them, and lower carbon footprints, for example, then you want to consider this as a possible solution. There is a significant amount of reduction in waste, which we've already mentioned as far as the future liability concerns being absolved, as well as the elimination in acquiring new virgin media. And so those costs continue to escalate as well, but you're going to be reusing the media, and therefore you'll avoid those as well. Smaller physical footprint, generally that's made for comparisons between granular activated carbon and ion exchange resin, be that single use or regenerable, but it's certainly smaller for the ion exchange. I mentioned the lower raw material consumption and the carbon footprint. And the big point that I want to bring forward is the bridge to tomorrow's destructive technologies. So regenerable resin can treat today's required volumes of PFAS impacted water. And we've fielded systems in place today for over 4 years operation time, one of which I will share with you. But B, the point being is all of the destructive technologies that Erica is going to speak to require a waste volume reduction of the waste stream, as well as increasing the concentration of PFAS. They have higher energy requirements and they have lower throughput. So they need that step. And the still bottoms that come out of the regenerable media provide just that step. So that is the bridge to tomorrow's destructive technologies that I wanted to emphasize. All right, regenerable resin, and what is it? It is very similar to a single-use ion exchange resin. It's a strong basic anion exchange resin, and it functions with a dual mechanism of removal, both an ion exchange component for the functional group, the charged functional group, as well as absorption for the hydrophobic tail. And so it will be removed. It has capacity and sorption affinity for the target solute, in this case PFAS, but really what we're focusing on is the desorption efficiency and the ability to remove the PFAS from the ion exchange resin. And so doing so requires some adjustment in the processes. And so it requires a little bit longer empty bed contact time. It is different than granular activated carbon and single-use ion exchange resin. So do not operate at, those empty bed contact times, but at a preferred empty bed contact time listed on this slide as 4.5, but somewhere between that, 3.5 to 5 minutes, probably not 5 minutes, 3.5 to 4.5 minute empty bed contact time for the regenerable product. And the regeneration process in and of itself requires a recipe as listed on this slide, or as called on this slide. And that's the solvent type. So the solvent type, it's an alcohol, but there's different alcohols we could use, a methanol or an IPA or an ethanol or combinations thereof, with a solvent component, a brine component. With the solvent component goes a brine component. And both the concentration of those two entities, as well as the contact time, as well as the number of bed volumes passed, all of these go into consideration how to achieve the most efficient regeneration for the media after it is exhausted and should be considered. This block flow diagram is of an active site that is in the Royal Australian Air Force, treating 200 gallons per minute. And through the blue lines here, I'm not sure if you can see my cursor, but you'd have your influent water going through a transfer pump and going through a pretreatment of granular activated carbon, followed by 3 vessels of ion exchange resin to remove the PFAS. The pretreatment protects the ion exchange resin. It does remove PFAS, but that's not its purpose. And so once this becomes exhausted with PFAS, that's not the purpose of it. It can remain exhausted and stay online. And treated water comes out on the effluent side. The regenerant side is this more brown-red color here, and the regenerant supply will then be passed through the ion exchange vessels, and leveraging that desorption efficiency that I referred to earlier will remove the PFAS, which will then be collected in this spent regenerant tank, which now consists of the alcohol, the brine, and concentrations of PFAS that are rather high, milligrams per liter. And then it will go through a distillation process where we'll be able to recover 99% of the solvent for subsequent regenerations. From after distillation, what remains is called the still bottoms, and that's what I'm offering as the ideal off-ramp to destruction, because it is a concentrated PFAS solution that is reduced in volume. That's what we're looking for a lot of or if not all of the destructive technologies. If we don't have those today, then we can go through a patented superloading process, which is, a mixed media, a bed of mixed media at extended contact times that will then remove the PFAS. The brine passes through, can be recycled, and out comes your solid waste. And we're treating, almost 1,000,000 to 1. 1,000,000 gallons of water treated is resulting in 1 gallon of solid waste that needs to be disposed of. So significant waste regeneration. All right, the first of three graphs here, three slides of data. All have the same x-axis, which is the date, and all have the same y-axis, which is the concentration of PFAS expressed in micrograms per liter. But please note that the scale on the bottom one has changed. It caps out at 1.4 micrograms per liter, whereas the other two cap out at 16 micrograms per liter. A lot of data here. I just want to mention a couple things. Top graph is the effluent from the granular activated carbon and the influent to the lead bed of ion exchange resin. And you can see the speciation of the PFAS, which are the green and the yellow denoting the PFOS and PFHXS, whereas the turquoise is PFOA. And that is what the treatment objective for this particular site was based upon, to remove them to the health-based guidance values for Australia, which is a 70 for the sum of the sulfonates and 560 for the PFOA. Moving on to the middle graph, you can see this is the effluent of the lead ion exchange vessel that we've removed all of the green, yellow, and turquoise. So we've obtained and achieved our treatment objective for this site. And all that remains are the shorter chain carboxylates. And moving on to the bottom graph, you can see here that we have, again, different scale. We have anywhere between 300 nanograms per liter up to maybe 1,000 nanograms per liter of the PFCAs that remain. If we wanted to target those and remove them, we could, and you would just increase your regeneration cycle. And these regeneration cycles are on average about every 3 or 4 months. So you would just increase your regeneration cycle if you needed to capture more mass. But the objective, again, is for those three components that the health-based guidance values are based upon. So across multiple regeneration cycles, the resin continues to meet the treatment objective, is the takeaway from the performance of this site. This slide, I'm sharing with you the amount of mass removed from the influent. This particular graph is one vessel, and there is a lead and a lag vessel, and then there are 2 trains of lead lag vessels. So this is one vessel of 4 that's at the particular site. And the roll-up data shows that the time between regenerations here is, on the course of 3 to 4 months, or averaging about 3.7 months. And then you can also see that we're removing on average about 650 grams per regeneration cycle. So since this has been in operation since 2018, we've removed over 16 kilograms of PFAS from the site, which is a sizable amount. And through since the 2018 startup date, we've done 17 regeneration cycles without losing performance in the media and without a degradation in the media integrity. The plastic bead is not breaking down and is not being compromised as we go through multiple iterations of the regeneration process. This last one's showing the mass balance and how much that the second column here is the mass collected or the removed from the influent waste stream at the water treatment plant. So that's the volume or the integrated area above the breakthrough curve to the influent concentration. That's what the data you saw on the previous slide. Whereas the third and fifth columns is the mass recovered. And so you take a grab sample from the regenerate solution and see how much PFAS you can account for. And we did 2 different methodologies to try to capture that. And that's what the other columns are showing, the unaccounted PFAS mass that we did not account for. And so some of it could have volatilized, some of it could have been on the chamber walls of the reactor, some of it could still be on the media. But what we see is, on average, through these 4 regenerations, that we see between 4 and 20% of the PFAS is unaccounted for and could possibly be remaining on the resin, but we don't see it climbing. We see it going down and we see it going back up. And so you see just consistent performance across multiple regenerations is the takeaway from this slide. So the takeaways for regenerable resin, and really it's an idea of feeding 2 birds with 1 scone. It's there are benefits that are being realized today, and there is a readiness for tomorrow. So I want to leave you with these 2 points that, it's an effective treatment that's generating minimal waste today, which is avoiding and limits the complications associated with the CERCLA designation when and if it comes, which avoids problems with increasing media costs and increasing disposal costs, the future liability concerns that we talked about. If you're not generating the waste, you're not going to have the problem of the waste later on. And then the reduced options for disposal with the April 22 moratorium that the DoD placed upon incineration. So, the options are becoming limited to deal with this waste as well. There are other benefits. I talked about the cost curves, the ESG metrics with the lower carbon intensity, the smaller footprint, and so forth. So on the graphic here shows, compared to granular activated carbon, how much waste would be generated in 1 year compared, 185 barrels of granular activated carbon spent requiring disposal versus 1 barrel of the regenerable ion exchange resin through the superloader process that I previously mentioned. But really the benefit also, the second bird that we're feeding, that is the destructive technologies for tomorrow. And so we have to have that volume reduction and concentration increase that we're looking for. And this provides it with those still bottoms. And so a lot of the destructive technologies have used and experimented, and we've provided our still bottoms for just that reason, to have this off-ramp that will lead into tomorrow's destructive technologies. Those are the 2 key points that I want to emphasize for the regenerable resin. All right, another solution, and I see I'm already quickly approaching on my allotted time, so apologies if I go rather quickly here, but the foam fractionation is another viable treatment technology. And the benefits of foam fractionation are listed on this slide. It's agnostic to elevated TDS levels or high natural organic matter content. And so if that is problematic to other waters, other technologies, then maybe foam fractionation should be looked at. Rather simple operation, few moving parts, low pressure differentials, low energy input, and that's going to result in lower operating costs. It could be hooked up with a treatment technology, and so you could go foam fractionation and then to a regenerable resin product, or as an off-ramp to a destructive technology. And so again, it could be an effective pre-treatment for difficult to treat waters. Not so much difficult to treat waters for foam frac, but difficult to treat waters for, conventional adsorbents or destructive technologies right up front. Landfill leachate, industrial wastewater, hotspots found in groundwater. So these are all ideal applications for foam frac, or at least to look at foam fractionation further. And so essentially you have an influent equalization tank, and that equalization tank then pushes the water into the top of the tank, and from the bottom of the tank, not necessarily shown here very well, air is injected. These are surfactants. They want to be at that air-water interface. They will partition into the foam. This foam is drawn out and put into a foamate tank. And then this foamate tank can then be either superloaded or moved on to a destructive or disposal technology. And clean water will come out from the bottom. And this bottom water can then be pushed through a secondary foam fractionator or a tertiary, can be operated in a recirculation fashion. But the concept is rather simple, which is really the beauty of foam fractionation. Here I've got one graphic that just or a video rather, that just shows you foam fractionation in action, which really, a video is 1,000 words. So yeah, I just think the video lends a lot in and of itself, just showing the scope and the scale of the project, as well as kind of the foam, what it looks like, and how the process is kind of operated. What inside of a trailer and mobile can be placed rather easily on a site and so forth. Here's some data from a recent landfill leachate treatment process that was operated by ECT2. And you can see that we have rather high removal, but you can also see that we have problems with the short chains, and in particular the carboxylates. And so you'll find this as a consistent theme through foam fractionation technologies, but it can be improved with the use of boosting agents. And so we are experimenting with different boosting agents, and with different waters, you get different results. And so some waters will foam rather easily on their own. Other times you have to add a boosting agent, and you'll find your removal efficiency greatly increased, such as this particular example here, where we went from 21 to 87% removal to the low to mid to upper 90s for PFAS removal efficiency. So work continues in this area, looking at different boosting agents, different concentrations, different residence times, and so forth. But the end question is, well, where does foam fractionation fit in? And the answer, as a good engineer would say, is it depends. And so that is based upon your influent concentrations of PFAS. That is affected by your background water chemistry, maybe not so much for the foam fractionation unit, but as mentioned previously, for the competing technologies that may have problems with this water chemistry, maybe foam frac would be the ideal pre-treatment step to consider. But also you have to consider your treatment objectives and whether or not those involve short chain PFAS, and if so, then this might not be the technology for you. Cost, relatively low, and a rather simple operation, and therefore it's certainly worth entertaining. And how best to entertain that is to conduct some field pilot testing that can inform kind of the suitability of the technology for your particular application and your particular water. But it is also an off-ramp to destructive technologies. And at this point in time is when I'm going to turn over the presentation to Dr. Houts, and Erica will walk us through the second half of the presentation, talking about some of the destructive technologies and the strengths and limitations. So with that, I thank you again for your time and your attention, and look forward to hearing about your questions and hopefully receiving some emails from you. Thank you very much.
Good afternoon, and welcome to the second part of our webinar today. I'm going to build on the different waste minimization techniques that Dave described, and discuss how we can pair them with a destruction solution so that we can achieve complete on-site PFAS treatment through a destruction phase. And as part of this presentation, I'm going to be presenting on both bench scale and pilot scale data that ECT2 has generated in collaboration with other organizations to achieve destruction of PFAS in ion exchange still bottoms. And I'm also going to be discussing the applicability of some of these technologies to foamate as well. So just to begin, I want to go over a couple of key concepts that I think are pretty important how we're going to think about PFAS destruction. First, I want to make sure that everybody understands the term still bottom. This is the end product of a regenerable ion exchange process. Once the resins are saturated with PFAS, we desorb them using a brine solvent solution, and then we evaporate the solvent away so that we're left with an aqueous high TDS solution that's very high concentration in PFAS. So we're using sodium chloride. Chloride is the counter ion to desorb the PFAS from the resins. As a result, we end up with more than 2% sodium chloride in our still bottoms, depending on kind of the exact recipe. We typically have somewhere between 2 and 5 grams per liter total PFAS. This does depend on regeneration frequency and treatment targets. Some still bottoms have color. You can see in the one that I'm showing on the right, which is literally a still bottom from sort of a bench scale distillation process. Looks sort of like a light coffee color. Not all still bottoms end up with color, but many do. Usually from humic substances, so it sort of depends on the influent chemistry. And then we also get inorganic anions that desorb off of the resins that also have an attraction to the resins, things like nitrate and sulfate. The pH tends to be neutral to basic, and then we have very low levels of solvent after the distillation process, sort of in the low milligram per liter range. Dave has already explained foam fractionation. What we're looking at is a still from that video he showed you. Some of the fomate up top. This is a material that condenses into a liquid. A couple things to note about fomate is that its background chemistry tends to resemble whatever was in the source water. So if we are fractionating a leachate or a groundwater, most of the characteristics of that water will be present in the foam as well. A couple things can change. We do often see a much elevated total suspended solids level in the fomate. And these sort of features can just dictate what sort of pretreatment might be necessary for a destruction technology. So depending on what you're applying foam fractionation to, it can really, influence that. And then finally, in terms of key concepts, what do I mean when I'm talking about PFAS destruction? Well, it's kind of context dependent. Sometimes I'm going to be talking about disappearance of individual compounds, and these are probably going to be forming transient intermediates. And sometimes I'm going to be talking about mineralization. And there I'm talking about destruction of all carbon-fluorine bonds to terminal CO2 and fluoride. I think it will be clear which one I'm referring to when I'm talking about it in the discussion. How we think about determining PFAS destruction, we use both a targeted analysis, so the types of analyses you guys are familiar with, most likely, methods like 1633 or 537. We have an additional method that we use to measure the ultra-short compounds, things like trifluoroacetic acid and trifluoromethylsulfonate. We also measure fluoride and total organofluorine using a combustion chromatography method. There's also gas phase analyses that can be a part of this process of determining true PFAS destruction. Things like FTIR can be used to evaluate gas phase products. In terms of treatment targets, I just wanted to mention that when we have an upfront concentration process, we don't really need to get down to nanogram per liter levels of destruction. If we're getting 2 or 3 orders of magnitude of destruction of our target compounds, that's likely going to be good enough because then we can just take that very low volume minimized liquid waste stream and pass it back to the front of our treatment process. So when we think about what we're looking for in a destruction technology, it does depend on whether we're talking about ion exchange still bottoms or on fomate. I would say there's more options available for fomate, although maybe more pre-treatment will be required for fomate. There's fewer constituents in ion exchange still bottoms, I would say in general, but we do have very high salt content. We've got that high sodium chloride level that we need to think about how that's going to affect the destruction process. So I'm going to be talking about that quite a bit through this presentation. We care about how well we can break down long-chain PFAS, compounds like PFAS, PFOA that typically have the most stringent regulatory targets. But separately, we also care about how well we can totally mineralize PFAS to fluoride and CO2. Some of these destruction processes, we start to see a big kinetic slowdown around PFBA, PFBS, and a much less sort of efficient destruction process. So that's another thing we're going to think about. And in terms of getting to mineralization, we do see that a treatment mechanism that's working in the bulk solution rather than at an interface is very desirable to get to mineralization. And this is just because the very short compounds lack a lot of the amphiphilic or hydrophobic characteristics that are involved in some of these destruction technologies. So we want to have manageable formation of undesirable byproducts or other reagents that might be used in the process. Negligible formation of partially fluorinated gas phase products. I would say this is kind of acutely on my mind just because I think this is at least the perceived issue with incineration, that the residence times or treatment temperatures or the combination of the two are not sufficient to fully destroy compounds, that some partially fluorinated products are emitted. I'm not making a comment on whether that's true or false for incineration in general, but I do think that's sort of the overarching concern around incineration as an ultimate PFAS destruction mechanism. Obviously, we care about O&M, want to minimize energy use. We want a process that is simple or at least won't require significant amounts of maintenance, and then we want a safe technology. So there are 5 different technologies that we've trialed at the bench or pilot scale. I'm going to go through each one of these in detail. There are some additional destruction technologies out there, but I think these actually pretty well cover maybe 70–80% of the offerings in the marketplace. So first I'm going to speak to electrochemical oxidation. This is treatment of an aqueous waste stream in an electrochemical cell that has a charged anode and cathode. The way that PFAS are destroyed in the cell, the critical or rate limiting step is direct electron transfer to the PFAS molecule at the anode. And then from there, other oxidative species that are generated in the electrochemical cell, things like hydroxyl radical, participate in the destruction of that perfluoroalkyl radical. We do see sequential chain shortening through most electrochemical oxidation processes, where we're going to move from a C8 to a C7 and on down the line. And critically for the sulfonates, you see once the sulfonate is cleaved that you get destruction through carboxylates or through carboxylate intermediates. There's different kinds of electrodes available. Some commercial providers are not very transparent about what they are as part of their confidential business information. Others are. I would say the two that are most typical for PFAS destruction that we see in the marketplace are Magnelli and boron-doped diamond electrodes. There's other kinds available. I think a graphene-based electrode that's been developed by Jelena Regenerable in Spain is really cool because we don't see formation of perchlorate with that particular electrode. But different kinds of electrodes, also different configurations of the electrochemical cell. There's pros and cons to each electrode in terms of efficacy, durability, and cost. I'm not going to get into that level of detail in this presentation. We do generally see in the data we've collected slower kinetics in the high TDS waters that are typical of still bottoms. Some TDS is favorable to serve as electrolytes, but we see that generally the levels in still bottoms are not super advantageous for the functioning of the electrochemical cell. And finally, just to highlight in terms of byproducts that we might be worried about, perchlorate's a big one. It is a manageable byproduct, but does require an additional treatment step. So what I'm showing in this slide are the results of a pilot scale demonstration that we did with AECOM on electrochemical oxidative destruction of our ion exchange still bottoms. On the right side, I'm showing a publication that resulted from this work where we're looking at the percentage removal of different PFAS in two different ion exchange still bottoms that resulted from that study. And just to kind of narrow in on a couple of take-homes, we see really great destruction of long-chain PFAS. We see worse destruction of short-chain PFAS. I think that's twofold. One, we're forming short-chain compounds as these longer compounds break down, so they're sort of transient products. And additionally, they are just have less affinity for the electrode, so less likely to participate in that the rate limiting step at the anode. So there's more optimization occurring, and I know that in particular our team AECOM present data with significant short chain removal and other applications, so it could partly be a phenomenon of still bottoms. Here is some bench scale data with a different electrode type, a boron-doped diamond electrode, and we treated two different solutions. They were both spiked with a lot of very short PFAS, all the way down to the shortest ones, TFA and TFMS. So these solutions were identical, except one had the sort of salt characteristics of still bottoms and the other one didn't. We saw much more rapid depletion of PFAS in the low TDS solution, so that's on the left. Please note we're looking at a log scale. So we saw, 3-4 orders of magnitude removal within 4 or 5 hours in that solution. We saw nowhere near that level of removal in the still bottom solution. So just gets at sort of the differences in kinetics and efficacy depending on the solution chemistry. The next technology that I want to speak to is non-thermal plasma. We have done a pilot with DMAX, which is affiliated with Clarkson University, Tom Holston and Selma Medetovic. It's an argon bubbling plasma reactor. It kind of functions, I would say, partly as a foam fractionator and partly as a destruction unit, where the argon, which is used to form the ionized plasma phase, is also used to bubble PFAS to that interface where the destruction reactions occur. So it occurs in the ionized gas interface. Both reductive and oxidative species are formed in the plasma, and we do see destruction of PFAS in that phase. Compared to treatment of groundwater samples, the higher TDS conditions of the still bottoms did result in a pretty big slowdown in the kinetics of destruction they increase the energy consumption per order of magnitude destruction, the EEO, by about 1 to 2 orders of magnitude. And that was really just a function of the slower kinetics. So the way that this plasma reactor was configured in this trial, there was both a high concentration reactor and a lower concentration reactor. I think there were 2 reasons why this particular configuration occurred. One, you can treat really rapidly the long chain compounds in the high concentration reactor, but because you're introducing such high concentrations that are typical, so remember starting with grams per liter potentially, you're getting kind of constant sorption and desorption from the reactor walls, which make it difficult to achieve ultra low levels of treatment. So when you move that largely treated solution into a lower concentration reactor, a lower concentration plasma reactor, you can achieve lower levels of destruction. So one thing to note, the left plot is a log scale, the right plot is a regular scale. And that's just sort of getting at the difference in kinetics of destruction from long chain to short chain. So over a similar duration, we saw multiple orders of magnitude reduction of the long chain compounds, where we're seeing, only 1-fold order of magnitude reduction for the short chain compounds. So this did work pretty well for the still bottoms, but we did have difficulty seeing mineralization. The third technology I want to speak to is supercritical water oxidation, or SQO. The way this works is that water, some type of a fuel source, and an oxidant is brought into a supercritical regime, where water essentially changes its typical character that we see under subcritical conditions. It becomes nonpolar, organics become highly miscible, so PFAS become highly miscible, as does oxygen. And so a lot of reactions that don't occur in a kinetically rapid way under subcritical conditions are favored under these conditions. So you can get rapid destruction of PFAS using hydroxyradical under a SQO regime. I would say SQO is highly challenged by high salt concentrations to result in reactor plugging and formation of oxides. There's also high corrosion potential. But I do think that SQO has a number of really good applications, including treatment potentially of fomate. I know that 374 Water has sold a unit for treatment of biosolids in Orange County. And in part, that's because some of these materials have, for one, a lower TDS content, and then also a lot of embedded energy, which helps with the inherent fuel source needed to make this reaction work. If you're working with a low energy content solution, you have to feed in a co-fuel. So another application for SQO that we're interested in is a little bit outside the context of this presentation, is treatment of spent media. So single-use resins or GAC can be treated using SQO. This is just a screenshot from an EPA publication where 3 different SQO providers treated dilute AFFF. And just really quick take homes on this. One, it treated the full range of PFAS, sort of independent of chain length. You see excellent removal of PFBA and of PFAS, and you also see excellent removal of total PFAS, 100 to 10,000 times removal over reaction time frames spanning likely seconds, and also effective on both sulfonates and carboxylates. So it is a really good solution for rapid destruction and mineralization. It is an energy-intense process, but can be mitigated somewhat by the use of heat exchangers. We worked with 374 Water recently to use their SQO unit to treat both low TDS solutions and high TDS solutions. I'm not going to get into the high TDS data because essentially it wasn't very compatible with the reactor. So while the initial results were quite positive, it just was not compatible for long-term operation of the reactor. But with the low TDS water, I do want to highlight that we saw really terrific PFAS removal for very short compounds. So TFA, which is the sort of pea green bar, TFMS, which is the final bar, the sort of hunter green color, and then a number of C4 and C3 polyfluorinated compounds. All of these compounds were depleted by at least 2 orders of magnitude within the typical residence time of the reactor, and likely greater levels could be achieved with a longer residence time. We didn't see great fluoride recovery in this case. We didn't see a good fluoride balance. I think this is just an ongoing challenge for the PFAS community in general, and certainly evaluating destruction technologies, but it's one that we're actively working to figure out whether there's a gas phase that we're missing, or if there's some other challenge with recovering fluoride. The fourth technology that I want to focus on is UV irradiated sulfite. And this is essentially a technique that is used to generate aqueous electrons in a solution which have a high efficacy of breaking down the sulfonates and the carboxylates, unlike oxidative species. Most of the work on this has been done by Jin-Young Liu's research group at UC Riverside, and we've also worked with them to generate some initial data in still bottoms. So the aqueous electron is very effective at abstracting fluorines off of the PFAS molecule. There's a different mechanism as well where it can interact with the sulfonate or carboxylate group, which leads to decarboxylation, hydroxylation, elimination, form sequential formations of shorter PFCAs in that case. This is a slower process. I suspect that with a higher wattage UV lamp, maybe this could be accelerated. I'm sure there's optimization that can occur. Also, the presence of iodide has been shown to increase the rates of reaction, but it's pretty easy to execute, and early data does suggest that it works well and under the conditions of still bottoms. And there are other, I should say, UV processes that can be used in a similar way, other kinds of photosensitizers to generate aqueous electrons. Typically, the aqueous electron cannot fully defluorinate most of these compounds. As you start stripping off fluorines, you're left with a couple of carbon-fluorine bonds whose then bond energies increase as you remove other fluorines from the molecule. But then basically you're left with a precursor or polyfluorinated compound, and those molecules are very susceptible to oxidative attack. So if you combine the reductive process of UV sulfite with an oxidative step, you can see complete defluorination. And that's what I'm showing in this plot from one of Jin-Young Liu's publications. The final technology I want to discuss is hydrothermal alkaline treatment. This is a technology that was developed for PFAS out of Colorado School of Mines. It's now offered commercially by a company called Aquaga, which is based in Tacoma, Washington. It has some similarities to SQUO. It's not as quite high of a temperature or pressure. It's still subcritical. So water still has its typical subcritical characteristics. Salts are highly soluble, for example. As a result, in general, this process has really good compatibility with the high TDS conditions of still bottoms. And the way this works is that solutions are amended with a high level of caustic or another base, but typically caustic, to bring the pH above pH 14. And under this high temperature and high pressure, you see a rapid nucleophilic substitution of hydroxide at the carboxylate and sulfonate groups, which leads to decarboxylation, desulfonation, and defluorination. At the end of the reaction, you do need to have some type of pH adjustment typically, or you can blend with your if you're taking it back to the influent, perhaps the volume differential is enough that you don't have to do much pH adjustment. But so it's a really rapid process, not quite as rapid as SQUO, but still a reaction that occurs kind of on the order of minutes to see multiple orders of magnitude removal, minutes to tens of minutes. And then we partnered with Aquaga to test our still bottoms. This is an industrial wastewater still bottom that contained high concentrations of, again, very short compounds. A lot of the data I've shown has been really focused on short chain compounds, ultra shorts. There's also a bit of PFAS and PFPA. And as we move from left to right, the reaction conditions become increasingly aggressive for each compound. So as we move from the leftmost bar to the rightmost bar. But what we can see under all of these different reaction conditions is that we're seeing almost 100% removal of all of these compounds, including trifluoromethyl sulfonate, which is admittedly one that UV sulfite struggles with. So we see really great removal of all of these really short compounds. Much like SQUO, we're seeing mineralization. We did see a fluorine mass balance based on fluoride greater than 100% due to the presence of other fluorinated compounds in these still bottoms that were not captured in the analyte list. So we saw a decent mass balance closure, but there's still more work to be done on that. But so great pairing with still bottoms. I wanted to briefly speak to the energy comparison with some of these different technologies. Incineration is sort of top of the list, and I'm generating these numbers from different literature-derived values, I should say. We're looking at EEO, so this is the energy consumption per unit volume to achieve 1 order of magnitude reduction. This does vary depending on the compounds. Typically, sulfonates have a higher EEO than carboxylates. It will depend on the waste characteristics. Additionally, we see some of these large ranges based on how much heat exchange is incorporated into the process to recover energy losses. But a couple of things. For the thermal processes like incineration, halt, and SQO, the major energy consumption occurs in heating the material. It's not so much in the duration of the reaction. So you can get more orders of magnitude removal without a substantially higher energy consumption. That's not true of processes like UV sulfite, electrochemical oxidation, and plasma, which the energy consumption really depends much more on the reaction time. Now, there are still scaling implications for, scale-up rather, implications for halt and SQO in terms of, time in the reactor duration, but did want to point that out. So just to conclude, as Dave kind of valiantly led off in the first presentation, an upfront concentration process is really helpful to generate a very low volume, high concentration PFAS waste. And that is really what makes destruction economically viable. Whether you're going from a milligram per liter to a microgram per liter or a microgram per liter to a nanogram per liter, for the same volume of waste, you're probably going to have a pretty similar energy use. That's kind of the whole concept behind EEO. So the smaller volume you can treat, the more the economics are gonna work out for pairing a destruction process. Both regenerable ion exchange resins and foam fractionation generate a low volume, high concentration PFAS waste. There are a number of destruction options available. Most of them are pretty great at destroying PFAS and PFOA. I would say some of them really struggle to get beyond PFBA, PFBS. They can with enough time, but the kinetics in that case, or time is sort of money and energy consumption and scale up. We've seen that halt, SQO, and UV sulfite are really promising for complete mineralization. And halt and UV sulfite in particular seem really promising for destruction of ion exchange stilotums. Whereas SQO, I would say, has more applications with fomate and with neat materials and things like biosolids. Probably most of these technologies would work quite well on fomate, but there may be some level of pre-treatment required depending on the waste constituents. So we've already done field demonstrations with electrochemical oxidation and plasma. We have more work planned with additional technologies and more bench scale evaluation ongoing. Our goal is to offer a complete on-site destruction solution where no PFAS waste has to leave the site, and we can get a good level of PFAS destruction on site. So I do want to acknowledge my coworkers at ECT2 and a number of people working in the destruction space that we have collaborated with, and our funding sources. And with that, I'll take your questions. Dave Kempisi unfortunately can't be with us today to answer questions, but I'll do my best to field questions from his portion of the presentation as well. Thank you.
Well, Erica, thank you so much for that wonderful presentation. And Dave, thank you as well. We are so pleased to have Erica on with us, and we are going to do our best to get to as many questions as possible in the next few minutes. I do want to say thank you to all of the attendees who did submit questions this afternoon or this morning, wherever you are in the world. We have had great participation from everyone on with us. So Erica, let's get started. And thank you to Nancy thanks for the presentation. It was a great one. So we appreciate all the feedback. All right.
Can you hear me okay, Doc?
Yep, I can hear you loud and clear. You are good. So let's start with one that actually just came in. Do any of the additional technologies investigate AOPs or UV ozone?
So I would say most of the chemical AOP processes have been pretty thoroughly investigated with PFAS. Generally, they're none of them are effective on the perfluoroalkyl sulfonates. There are some persulfate activated techniques that are effective on the carboxylates at lower pH, and some of these are effective on partial breakdown of precursors as well. As I mentioned with, for example, with the UV sulfite technology, sometimes they can be used as sort of a polishing treatment.
Got it. That makes sense. So thank you for going into that. How much? Let's see. Let's do a different one now. Sorry, I'm scrolling through all of these, and we've had so many wonderful questions come in. So we do appreciate it. In the Lang study performance histogram, it showed one instance of negative removal. How is that possible?
So that's because there's transient formation of shorter chain products, both from the longer chain compounds that we're directly measuring and from precursors. So it's just sort of a function of that. That would be why.
Okay. Is that something common, or does it happen, in your experience frequently?
Yes, it's pretty typical to see transient formation of the shorter chain compounds, which do tend to hang around longer, as we've discussed. They're sort of kinetically more hindered to destruction with some of these processes. And then also, yes, it's quite typical to see unmeasurable polyfluorinated compounds, or maybe they're measurable, non-measured polyfluorinated compounds present in a number of these concentrates.
Got it. All right. Thank you for going into a little bit more detail there. Let's talk a little bit about Foam-X. Is Foam-X a batch or flow-through continuous process?
It's a flow-through process. We do have batch units that we use for testing in the lab, but at the commercial level, it's flow-through.
Okay, great. Thank you. Short and sweet, getting to that answer. Well, I know we have a lot of questions that have come in. I wish we did have more time to go through them, but I do. Erica, I think I just want to end with you giving us a couple of big takeaways for our attendees today before we wrap up.
So
sorry, I know I put you on the spot there.
I think the takeaways are that there are a couple of different options to achieve concentration of PFAS into a separate waste stream that can be more easily managed with destruction, and that depending on the specific treatment targets, there are a range of options available. Some are more commercialized than others, and I would say some are more scalable than others. But it's an area of rapid progress, and we definitely see opportunities to pair with our existing systems in the marketplace now.
I think that's a perfect way to end today's event. And we've had a couple questions come in about contact details. In your attendee console, you'll be able to find the details in order to contact both Erica and Dave. At any time, you can also email us to submit additional questions. Don't worry if you did submit a question today and we didn't answer it, we didn't get a chance to answer it. The team at ECT2 and Montrose will get a copy of all of them. So Erica, I want to thank you again, and Dave, who wasn't able to join us this afternoon, but we do appreciate the work that you put into the presentation. At this point, we are going to conclude the webinar, and yes, before you ask, and I know I mentioned it at the beginning, but this event will be available on demand for all registered attendees. We hope everyone has a wonderful rest of the day. Thanks, Erica.
Thank you. Bye.
Bye.